This is a lump of iron. And this is a neural network. One is a rock. The other is a piece of software. They were invented a century apart by people trying to solve completely unrelated problems. There is no reason on Earth they should have anything to do with each other. And yet, if you write down the mathematics that governs the rock, and then the mathematics that governs the software, you get the same equation, not a similar one, the same one. It's about what a neural network actually is underneath, and the answer is 100 years old, and it comes from the study of magnets. We'll build the bridge in 3 spans: a magnet that learns to agree with itself, a memory that is nothing but a shape, and the empty vacuum of space, which has exactly the same statistics as a neural network with its weights set at random. It's 1920. The German physicist Wilhelm Lenz hands a problem to his student, Ernst Ising. Explain magnets. Here's the thing to explain. A block of iron is made of atoms. Each atom's electrons generate a tiny magnetic field of their own. Its spin, and roughly speaking, a spin has 2 choices, up or down. Ising schematizes the whole block as a grid. Every site holds 1 spin, up or down, and then he asks the only question that matters. How does this grid behave over time? First rule, the room is warm. Heat makes spins flip at random. Second rule, any 2 neighboring spins would rather point the same way. Agreement is cheap. Disagreement costs energy. So let's actually count. Take any arrangement of the grid. Look at every neighboring pair and count the disagreements. That number is the energy. Lots of arguing, high energy, everyone agreeing, low energy. That's the entire model. There is nothing else in it. A tiny grid, just 4 spins, has 16 possible arrangements. We can draw all of them. And every one of them has an energy, which means every one of them has a height. Line them up by height, and something appears that isn't in the physics at all. A landscape. So the marble's position is the grid's arrangement. Its altitude is the energy of that arrangement. 2 things welded together. 4 spins gave us 16 configuration. 100 spins give us 2 to the 100. More arrangements than there are atoms in the observable universe. We can't draw that landscape. Nobody can, but the marble doesn't care. It just rolls downhill. Release it anywhere, and it rolls toward lower ground, which means the grid settles and the spins agree, and patches of agreement spread. Physicists call them domains. And now the strangest part of the whole model. The part Ising himself never found. Turn the temperature up slowly. Cold, and the domains freeze into one giant block of agreement. Hot, and they shatter into static. But at one exact temperature in between, the domains stop having a size. Patches inside patches inside patches, at every scale at once. The iron doesn't choose between order and chaos. It does both forever, all the way down. And here's the thing worth holding on to. At that critical point, iron behaves identically to a completely different magnet made of completely different atoms. It behaves identically to water at its critical pressure. Same numbers, same exponents, the materials have nothing in common. And at the critical point, none of that matters. The details wash out. Physicists have a word for this: universality. Remember it. Add an external field, and every spin falls into line. The block becomes a magnet. Ising's toy explains real iron, and then it sits there, mostly ignored for 60 years. John Hopfield is a physicist who has drifted into biology, trying to work out how a brain remembers anything. And he looks at Ising's magnet and asks a question nobody had asked. In the magnet, the couplings between spins are fixed. Nature chose them. Iron is iron. Hopfield's question was, what if we choose them? What if the numbers that say which spins want to agree? What if those were ours? Rename the pieces. The spins become artificial neurons. On or off. The couplings become weights. A positive weight pushes 2 neurons to agree. A negative weight pushes them apart. A 0 weight means they ignore each other entirely. That's the whole vocabulary. And the energy of this network is the same function, same shape, different letters, which means it has a landscape, and the network rolls down it, exactly like the iron did. But now watch what the inversion buys. Change a weight, and the landscape moves. Invert 2 of them, and the hill the marble was sitting in becomes the hill it rolls off. We are not observing this landscape anymore. We're holding the chisel. So dig, pick any pattern you like, any arrangement of on and off, and set the weight so that the landscape has a well exactly there. Now release the network anywhere nearby, and it has to roll into your pattern. It has no choice. That's a memory, not a file, not an address, a hole in a landscape. And the recipe for digging is almost insultingly simple. For every pair of neurons, if your pattern wants them to agree, make the weight positive. If it wants them to disagree, make it negative. Add up one term per memory. That's it. That's the whole learning rule. Now overfill it. Dig a second well, a third, a tenth. And for a while it works beautifully. But keep going and the wells start to touch. They merge, and the landscape grows valleys you never dug. Blends of your memories, sitting in holes of their own, waiting to catch the marble. Push past about 14 memories per 100 neurons, and the whole thing collapses into mush. The network doesn't fail gracefully. It starts confidently remembering things that were never put in. Hopfield's network is a ring, everything talking to everything. Over the following decades, Geoffrey, Hinton, and others straightened it out. Stacked the neurons in layers. Let information flow one way. Tune the weights not by a handwritten rule, but by showing the thing millions of examples and nudging every weight slightly toward being less wrong. Same objects, same energy, same landscape. We just got very, very good at digging. So far, physics has been lending ideas to A. A magnet gave us an energy gave us a memory. That's one bridge, and it's the one that won the Nobel. But there's a second bridge. It was found much more recently. It runs in the opposite direction, and it is much stranger. Forget everything about brains for a minute. Here's a small network. 2 numbers in, 1 number out. That's all it is. A function, 2 numbers in. So call them coordinates. A point on a plane, and 1 number out, which will draw as a height above that point. Do that for every point, and the network stops being a diagram. It becomes a landscape, a surface. In physics, that object has a name. It's a field, and fields are not exotic. The temperature in this room is a field, a number at every point. So is the wind, so is gravity. A field is just a number everywhere. Now, the move that makes this whole thing work, and almost nobody does it. Every explainer varies the input and keeps the network fixed. We're going to do the exact opposite. Pin one point, leave it there, and rebuild the network underneath it, over and over, with fresh random weights every time. Do it 1,000 times. And instead of clearing the screen between each one, leave them all up. And look, some values come up far more often than others. The network's output at this one point isn't a number. It's a distribution. Now widen the network. More neurons in each layer. 10, 50, 500. And watch what happens to that lumpy, ragged distribution. And here's where most tellings say, surprisingly, and move on. But it isn't surprising. It's the oldest result in statistics. Look at one neuron in that wide layer. What does it actually do? It takes 1,000 incoming numbers, each multiplied by its own random weight, and it adds them up. It's a sum of 1,000 independent random things. And there is a theorem, the central limit theorem, which says that when you add up enough independent random things, it does not matter what any of them looked like individually. The sum is a bell curve. Roll dice, it's a bell curve. Flip coins, bell curve. Add up 1,000 random weights, bell curve. The network isn't doing anything clever. It's wide, so it's summing, and summing is what makes Gaussians. One more thing, and it's the thing that makes this a field rather than just noise. It isn't only that each point has a bell curve, it's that nearby points have correlated bell curves. Ask how much the value here tells you about the value there, and you get a function. Physicists would call it a 2-point function. Statisticians call it a kernel. And that single function contains everything the random network knows about shape. Radford Neal proved this in 1995 as a graduate student of Geoffrey Hinton. As it happens, an infinitely wide neural network with random weights isn't approximately a Gaussian process. It is one. And notice what just happened. We widened the network and the details stopped mattering. The architecture washed out. Where have we heard that before? This is quantum field theory, our deepest description of what the universe is made of. And its central claim is this: there are no particles. Not really. There are fields filling all of space, and their values fluctuate at random, everywhere forever, even in perfect vacuum. What we call a particle is a ripple, a disturbance traveling through a medium that is already shaking. The simplest possible version, the one physicists solve first, and the only one they can solve exactly, is a field where the ripples ignore each other. They pass straight through. No collisions, no interactions. Physicists call it a free field. And here is the fact that ties the whole film together. In a free field, the value at any point fluctuates according to a Gaussian. And the correlation between 2 points, how much the ripple here knows about the ripple there, is a single function that physicists have been calculating since the 1940s. They call it the propagator. Left, an infinitely wide neural network, a piece of software with its weights set at random. Right, the vacuum of empty space. Same measuring instrument. Same bell curve. These two things are not similar. On this measurement, they are indistinguishable. But the real universe isn't free. Ripples do hit each other. And physicists handle that by starting from the free field and adding corrections. Small terms in a long series, each one a little harder than the last. And the real neural network isn't infinitely wide either. It's got 500 neurons, or 50,000, a big number but not infinity. So its distribution isn't perfectly Gaussian either. It's slightly off, and you fix it by starting from the Gaussian and adding corrections. Small terms in a long series, each one a little harder than the last. Not similar corrections, not analogous corrections. The same corrections, with the same structure, organized by the same expansion. The width of your neural network is playing the role of the strength of a physical interaction. So there's a dictionary, and it isn't poetic. It's line by line. The kernel of your network is the propagator of the field. 1 over the width is the coupling strength. Finite width corrections are interaction corrections, and the diagrams physicists invented to organize those corrections. Feynman diagrams organize the neural network ones too. Same diagrams, same combinatorics, same series. This correspondence was written down in 2020 by James Haverson, Anindita Mady, and Keegan Stoner at a new institute set up to point physics and machine learning at each other. And here's why anyone should care. So some physicists have started using the dictionary backwards. Not physics to explain to compute physics. They can already reproduce a free field exactly. They've done fields with interactions. The 5-4 model, where ripples collide in pairs. They've done conformal fields. It cannot handle a realistic situation yet. Not close, but it is a genuinely new way to attack a 60-year-old wall. And it runs the other way too. If finite width corrections really are interaction corrections, then the tool physicists built for interactions works on neural networks. Feynman diagrams, invented in 1948 to describe electron scattering, now being drawn for a piece of software. The traffic is already heavy in both directions. Physics uses A to denoise gravitational waves, to hunt new particles in collision data, to find new materials, to simulate phase transitions, to reconstruct galaxies bent by gravitational lensing, to map dark matter. Uses physics, energy landscapes, field theory, renormalization. To get some purchase on a technology we built and do not understand. But I don't think the applications are the interesting part. Here's the interesting part. Why should any of this be true? Why should a rock and a memory and the vacuum of empty space share a single equation? It isn't a coincidence, And it isn't mysticism. We said the word 10 minutes ago. Watching iron sit at its critical point and behave exactly like boiling water. Universality. When you have a great many simple things, interacting locally, and you stand far enough back, almost everything about what they are washes out. What survives is a shape. And the shape does not care whether the simple things were atoms, or neurons, or ripples in a vacuum. Physics has known this for 50 years. It's the reason a physicist can look at a magnet and see a memory, and look at a memory and see empty space. Artificial intelligence isn't borrowing from physics. It fell into the same universality class. It was always going to be there. We sealed this box in the middle of the film, a network abstracted into a function, the thing everyone calls a black box. It isn't opaque because it's complicated. It's opaque because we've been looking at it with the wrong instruments. And the right ones have been sitting in a physics department for a century. A lump of iron and a neural network. They have everything in common.